This lesson, 117, is a little bit of a step from the last lesson 113 where we learned about direct and indirect variation. Now they're saying that those statements aren't always as simple as you learned back in 113. Of course, it's never as simple as you think it should be, or as you want it to be, right? But it doesn't have to be too complicated. So let's talk about what we see in the book. So you should have your book open to 493 and look at the statements that they give us. One statement says, the weight of a body varies inversely with the square of the distance of the center of the earth. Now, if you read that to someone or explained that to someone, it would make you sound very, very smart if you just read that statement out loud. The weight of a body varies inversely with the square of the distance to the center of the earth. Now, the neat thing is as you're getting further and further in algebra, you're able to take complicated, nerdy sentences like that and put it into something very simple or legible, something that you can understand. So we look at the implied equation to the right, where it says the weight of a body varies inversely. So you say W equals. Now, inversely meant K was over the X, right, or the other variable. So K divided by the square of the distance, so you'd say D squared. So I want you to look at those statements and then the implied equation and see that what looked super complex at the beginning isn't too bad when you look at the implied equation. The next statement said the distance required to stop is directly proportional to the square of the velocity. So they get the equation D equals KV squared. And so I want you to be able to figure out if you can understand where the implied equation came from, how they got that set up. The next one says the price of diamond varies directly as the square of its weight. So P equals KW squared. The strength of the field is inversely proportional to the cube of the radius. S equals K over R cubed. Okay. Once you get the setup of the implied equation, they are solved exactly the same way as the ones that we did in lesson 113. It's just recognizing the statement, figuring out the equation for it, and then solving it like we did in the past. All right, so example 1, I said read from the book, I think, because I did not want to have to write all that out. So let's read it together. The distance required for an automobile to stop is directly proportional to the square of its velocity. Okay, so that actually was above. We first write the equation. D, the distance varies directly, so we know it's not going to be a fraction, not a division, it's a multiplication, varies directly by the square to the square of it, or sorry, it doesn't say varies directly, it says is directly proportional to the square of its velocity. So there's your equation. And once we have that, we're halfway home. The next sentence says, if a car can stop in 200 meters, okay, so that's a distance, at 20 kilometers per hour, so that's a velocity, what will so we just take that first statement. If the distance is 200, the velocity is 20 squared. Now we get to find our constant, our K, figure out what K is. So we're going to simplify that. 20 squared is 400 K. Okay, so we divide both sides by 400, and that's 1/2. So we're going to say 0.5 equals our constant K. Now the last sentence says, the last part of that last sentence says, what will be the required stopping distance? So we need to find our D if their velocity is 28 kilometers per hour. So now we use this, plug it back in. I'm going to move it over here though, because I started out too. So what is the distance? Now we know our K. If the velocity is 28 kilometers per hour. And there we go. We just multiply, we square that. Don't multiply it by 2. It's 28 squared. And then times 0.5. And when we do that, when we calculate that out, we get 392 meters. Okay, and these are actually interesting for when we do learn to drive, is that what it means is it takes 392 meters to stop if your car is going 28 kilometers per hour. Now it's a little weird because we don't do kilometers or meters in the US, so this is an interesting equation when we use miles per hour and miles to see how long it really takes to stop a car when you're traveling at a fast speed. So it'll help you be a better driver when you understand that it's hard to stop fast. All right. Example 2, a distance a body falls. Now, I don't think they're talking about a dead body. I think they're just talking about an object, but maybe it's a body. Hey, if it's more fun to think about it being a body, then let's have it be a body, a human body. The distance a body falls varies directly, so that's going to be a multiplication, varies directly as the square of the time that it falls. So that means the next sentence says if it falls 144 feet in 3 seconds, so it falls 144 feet in 3 seconds, we find our k and then answer the next question. So that's 144 equals 9k. Divide both sides by 9. And 9 goes in there. K equals 16. And now we take that again. How far will it fall in 10 seconds? So it's probably going to fall pretty far. So there it is. So it's 16. Oops. Sorry, I was getting ahead of myself. 16 times 100, which is just 16, 2 zeros, so 1600 or 1,000 feet, 600 feet. There we go. Last one. Oh, I thought there was, there it is. I couldn't find it. Okay, the weight of a body on or above the Earth's surface varies inversely. Sorry, I'm trying to move this at the same time. With the square of the distance from the body to the center of the Earth. Okay, that sounds terrible, very complicated, and very nerdy. So let's take that, simplify it. The weight of a body on or above the Earth's surface varies inversely. So we put the k on top, with the square of the distance from the body to the center of the Earth. So there is our equation. If the body weighs 10,000 pounds, so I guess we're not talking about a human body because I don't think that is possible. That'd be very uncomfortable. At a distance of 5,000 miles from the center of the Earth. Now we find our k, and how we do that is, that's the same here. I'm going to bring it up here. If you can see it. 10,000 equals k, and then 5,000 squared. So once we get it to here, that 5,000 squared is 25, and we're going to have 6 zeros. So 25 million. Now you can see all these zeros, and we want to go into scientific notation once it gets that big. So when we do that, let me show you the long way. That's like 25, 6 zeros, 7, 8, 9, 10, with 10 zeros. So we can write that out or write 10 to the 10th equals k. Just so you know, I multiply both sides by 25 million. So now we've got our k. 25 times 10 to the 10th, or that's the same as 2.5 times 10 to the 11th, but we're going to leave it like that. And now finish the rest of the sentence. It says, how much would it weigh 50,000 miles from the center of the Earth? So Now we're looking at weight equals K, and it's going to be 50,000 miles. So that's going to be a big one, right? Well, kind of, these are going to reduce. So the book takes this 50,000 and squares it, and when we do that, we get 25, and if we square it, we get 1, 2, 3, 4. We're going to have 8 zeros. Okay, so now we've got something that you guys know how to reduce. In fact, this is kind of nice, right? And so it's just 10 to the 10th over 10 to the 8th. Well, 10 minus 8 is 2. So our final answer is 1 times 10 to the 2, which is actually 100 pounds. Okay, so if that went too fast, go back and look at it. If it got confusing with scientific notation, I want you to review it because I really want you to be able to understand this. But really, I count the zeros, and that's how many, that's the exponent that gets attached to your 10. Now I'm going to go ahead and do practice A. You're going to do it on your own, so pause me, do it, and see if you get it right. Okay, and I will kind of do it quietly. It's an inverse. I guess I won't do it quietly, I'll talk. Varies inversely with the square of the distance. So we're doing just like the one we did before. If the body weighs 50,000 pounds at a distance of 6,000 miles from the center of Earth, we have to find our K. Well, if we put this in the scientific notation, since we have so many zeros, 6,000 squared is going to be 36 million. So that's 36, sorry I'm having some problems here, 36 times 10 to the 6th, because we've got 1, 2, 3 zeros and double those. Okay, and this we're just going to say 5 times 10 to the 4th, so that it's going to be easier to calculate. So now we multiply both sides by 36 times 10 to the 6th. Okay, and when we do that, those guys go away, so now we're just going to multiply that. 36 times 5. Okay, I'm pretty sure I already did that somewhere, but 180. Alright, so we get 180 times 10 to the 10th equals K. So there's our K. And we're going to go ahead and read the next sentence. It says, if it is, what's it going to weigh if it is 25,000 miles away? So take our K, 180 times 10 to the 10th, and we are 25,000 miles from Earth. Okay, so we're going to have to square 25. Okay, do we know what 25 squared is yet? Is it one you have memorized? I hope so. So 25 squared is 625. So that's 625 times, I don't know why I'm giving it a parenthesis. I'm going to take that off. 625 times 10 to the 1, 2, 3, 4, 5, 6. So 10 to the 6th. Okay, I'm letting you guys use a calculator. If you do 180 divided by 625, you get 0.288 times 10 to the 4th. Okay, so let's simplify that out or get rid of scientific notation. Times 10 to the 4th. That means this moves over 4 times, so we get 2,880 pounds. Oh, that Again, if you got to here, I'm letting you use a calculator. 180 divided by 625 equals 288. So I sure hope you watched the video, because you wouldn't know that I was giving you a break with the calculator unless you watch my video. So you should probably watch the videos. All right, and there are exactly 3 more videos left to watch. So hang in there and have fun.